A soap bubble is an extremely thin film of soapy water enclosing air that forms a hollow sphere with an iridescent surface. Soap bubbles usually last for only a few seconds before bursting either on their own or on contact with another object. They are often used for children's enjoyment, but they are also used in artistic performances. Assembling several bubbles results in a foam. When light shines onto a bubble, it appears to change color. Unlike those seen in a rainbow, which arise from differential refraction, the colors seen in a soap bubble arise from interference of light reflecting off the front and back surfaces of the thin soap film. Depending on the thickness of the film, different colors interfere constructively and destructively. Mathematics. Soap bubbles are physical examples of the complex mathematical problem of minimal surface. They will assume the shape of least surface area possible containing a given volume. A true minimal surface is more properly illustrated by a soap film, which has equal pressure on inside as outside, hence is a surface with zero mean curvature. A soap bubble is a closed soap film. Due to the difference in outside and inside pressure, it is a surface of constant mean curvature. While it has been known since 1884 that a spherical soap bubble is the least area way of enclosing a given volume of air, it was not until 2000 that it was proven that two merged soap bubbles provide the optimum way of enclosing two given volumes of air of different size with the least surface area. This has been dubbed the double bubble conjecture. Due to these qualities, soap bubbles films have been used with practical problem-solving application. Structural engineer Fry Otto used soap bubble films to determine the geometry of a sheet of least surface area that spreads between several points, and translated this geometry into revolutionary tensile roof structures. A famous example is his West German pavilion at Expo 67 in Montreal. Physics. Merging equals. When two bubbles merge, they adopt a shape which makes the sum of their surface areas as small as possible, compatible with the volume of air each bubble encloses. If the bubbles are of equal size, their common wall is flat. If they aren't the same size, their common wall bulges into the larger bubble, since the smaller one has a higher internal pressure than the larger one, as predicted by the Younger Laplace equation. At a point where three or more bubbles meet, they sort themselves out so that only three bubble walls meet along a line. Since the surface tension is the same in each of the three surfaces, the three angles between them must be equal to 120 degrees. Only four bubble walls can meet at a point, with the lines where triplets of bubble walls meet separated by cos 1, a 1/3, a per mil 109.47 degree. All these rules, known as Plato's laws, determine how a foam is built from bubbles. Stability equals, the longevity of a soap bubble is limited by the ease of rupture of the very thin layer of water which constitutes its surface, namely a micrometer thick soap film. It is thus sensitive to drainage within the soap film. Water falls down due to gravity. This can be slowed down by increasing the water viscosity, for instance by adding glycerol. Still, there is an ultimate height limit, which is the capillary length, very high for soap bubbles, around 13 feet. In principle, there is no limit in the length it can reach. Evaporation, this can be slowed down by blowing bubbles in a wet atmosphere, or by adding some sugar to the water. Dirt and fat, when the bubble touches the ground, a wall, or a skin, it usually ruptures the soap film. This can be prevented by wetting these surfaces with water. Soap bubbles as unconventional computing. The structure of soap films makes that volumes cannot only be enclosed as spheres, but as in virtually any shape, for example in wire frames. Therefore, many different minimal surfaces can be designed. It is actually sometimes easier to physically make them than to compute them by mathematical modeling. This is why the soap films can be considered as analog computers which can outperform conventional computers, depending on the complexity of the system. Bubbles in education. Bubbles can be effectively used to teach and explore a wide variety of concepts to even young children. Flexibility, color formation, reflective or mirrored surfaces, concave and convex surfaces, transparency, a variety of shapes, elastic properties, and comparative sizing, as well as the more esoteric properties of bubbles listed on this page. Bubbles are useful in teaching concepts starting from 2 years old and into college years. A Swiss university professor, Dr. Natalie Hartzell, has theorized that usage of artificial bubbles for entertainment purposes of young children has shown a positive effect in the region of the child's brain that controls motor skills and is responsible for coordination, with children exposed to bubbles at a young age showing measurably better motion skills than those who were not. Fun. Use in play. Soap bubbles have been used as entertainment for at least 400 years, as evidenced by 17th-century Flemish paintings showing children blowing bubbles with clay pipes. The London-based firm A&F Pears created a famous advertising campaign for its soaps in 1886 using a painting by John Everett Millais of a child playing with bubbles. The Chicago company Chemtoy began selling bubble solution in the 1940s, and bubble solution has been popular with children ever since. According to one industry estimate, retailers sell around 200 million bottles annually. Colored bubbles. A bubble is made of transparent water enclosing transparent air. However, the soap film is as thin as the visible light wavelength, resulting in interferences. This creates iridescence which, together with the bubble's spherical shape and fragility, contributes to its magical effect on children and adults alike. Each color is the result of varying thicknesses of soap bubble film. Tom Noddy gave the analogy of looking at a contour map with the bubble's surface. However, it has become a challenge to produce artificially colored bubbles. Byron, Melody and Enoch Swetland invented a patented non-toxic bubble that glow under UV lighting. These bubbles look like ordinary high-quality clear bubbles under normal lighting, but glow when exposed to true UV light. The brighter the UV lighting, the brighter they glow. The family sold them worldwide, but has since sold their company. Adding colored dye to bubble mixtures fails to produce colored bubbles, because the dye attaches to the water molecules as opposed to the surfactant. Therefore, a colorless bubble forms with the dye falling to a point at the base. Dye chemist Dr. Rams Sabnis has developed a lactone dye that sticks to the surfactants, enabling brightly colored bubbles to be formed. Crystal violet lactone is an example. Another man named Tim Keogh invented a colored bubble which loses its color when exposed to pressure or oxygen, which he is now marketing online as Zibbles, which are non-toxic and non-staining. In 2010, Japanese astronaut Noko Yamazaki demonstrated that it is possible to create colored bubbles in microgravity. The reason is that the water molecules are spread evenly around the bubble in a low-gravity environment. Freezing. If soap bubbles are blown into air that is below a temperature of 15 degrees Celsius, they will freeze when they touch a surface. The air inside will gradually diffuse out, causing the bubble to crumble under its own weight. At temperatures below about 25 degrees Celsius, bubbles will freeze in the air and may shatter when hitting the ground. When a bubble is blown with warm air, the bubble will freeze to an almost perfect sphere at first, but when the warm air cools, and a reduction in volume occurs, there will be a partial collapse of the bubble. A bubble, created successfully at this low temperature, will always be rather small. It will freeze quickly and will shatter if increased further. Some evidence shows that soap bubble can be frozen at 14 degrees Fahrenheit. To avoid soap bubble destruction, it is recommended to use cold air, but not warm air from the mouth. Art. Soap bubble performances combine entertainment with artistic achievement. They require a high degree of skill. Some performers use common commercially available bubble liquids while others compose their own solutions. Some artists create giant bubbles or tubes, often enveloping objects or even humans. Others manage to create bubbles forming cubes, tetrahedra and other shapes and forms. Bubbles are sometimes handled with bare hands. To add to the visual experience, they are sometimes filled with smoke, vapor or helium and combined with laser lights or fire. Soap bubbles can be filled with a flammable gas such as natural gas and then ignited. Gallery of a soap bubble artist at work. See also, anti-bubble, bubble pipe, foam, Joseph Plateau, stretched grid method, Tom Noddy, where area Eurofilance structure. References. Further reading, Opry, John. The Mathematics of Soap Films, a Euro Explorations with Maple. American Mathematical Society. ISBN 0-8218-2118-0, Boys, CV Soap Bubbles and the Forces that Mold Them. ISBN 0-486-20542-8. Classic Victorian Exposition, based on a series of lectures originally delivered before a juvenile audience. Eisenberg, Cyril. The Science of Soap Films and Soap Bubbles. ISBN 0-486-26960-4. Noddy, Tom. Noddy's Bubble Magic. Pioneer bubble performers' explanations created the modern performance art. Stein, David, How to Make Monstrous, Huge, Unbelievably Big Bubbles. Formerly the Unbelievable Bubble Book, it started the giant bubble sport. ISBN 978-1-57054-257-2. External links, videos of bubble and droplet interactions, a more detailed scientific explanation, performances with bubbles and giant bubbles.